some folks who are going to be playing and singing with us tonight. Miss Emmylou Harris. And Miss Bonnie Raitt. And Mr. Jesse Winchester. I seen the bright lights of Memphis and the Commodore Hotel, and underneath the street lamp I met a Southern belle. Oh, she took me to the river where she cast a spell, and in that southern moonlight she sang a song so well. If you be my Dixie chicken, I'll be your Tennessee lamb. We can walk together down Dixieland, down Dixieland.
Okay. Good afternoon and welcome to this session. I know I'm competing with good lunch when your blood tends to flow downwards in your brain. So I try to be a little more animated. So in this session, I'm going to talk about graph mining with Apache Giraph. My name is Jay Tang from PayPal. Okay, this turn up? It is not moving. Ah. Still, excuse me.
Did you guys look into the other solution between like Graph Lab or?
I'll talk about it, yeah. Okay, still no luck to advance the slides. Okay, great, thanks. Excuse me. I'm going to start the graph with a little introduction of myself and what kind of work, what kind of problem we have at PayPal in terms of the kind of data we deal with and the volume of the data. Then we're going to focus on more like some of the unique nature of the data that is different from the traditional table-oriented data format that gives rise to the set of graph-oriented approach to look at data. And we'll discuss what kind of graph mining solutions we'll be looking at, and what are the reasons why we choose one particular graph mining engine versus other. I will focus most of the time of this talk on the core use cases. In this case, I will talk about risk mitigation, fraud detection use cases. PayPal as a financial service organization, managing risk fraud is a very big part of it. $1 of fraud loss prevention is equal to $1 of profit. That's much more important to have an extra $1 of sales. I will go end of the session talk about the lessons we learned, using a graph mining engine like Apache Hadoop, and what are the unique challenges it faces due to the context of problem domains, and some of the system level challenges we faces due to the nature of a big data environment. And I'll discuss briefly about what are the future works we'll be doing in this space. Okay, just a little bit about myself. I'm a director of a big data platform, and I know it's an overloaded word. In general, in a very simple, I lead a Hadoop engineering organization for PayPal, And we cover a wide range of work, not only in general Hadoop core technology, but graph mining, real-time analytics. And this is something we feel it has a potential to help us solve a lot of pertinent use cases. About myself, I've been doing enterprise software, so internet software in the Valley for about almost 2 decades. And I've been focusing most of my career on data. I was a member of the original Hadoop team at Yahoo that developed and managed one of the world's largest Hadoop cluster at the time. That was a few years ago. And throughout my career, I've built data warehousing or relational data product at most of the database companies. Okay. So next, I want to talk a little bit, before we start to talk about the graph mining problem, let's go ahead and take a step back, look at what kind of data problems we face. And that is a very important context to have. Okay. PayPal has its own unique set of big data problems. So let's talk about what does PayPal do? Now, most of the people know that PayPal is an online payment service provider. From last year, PayPal made a very strategic move going into offline and mobile payments. About well over 100 million customers. That's at the end of Q1 2013. We do approximately like $160 billion of payment processing annually. And this is the data I take from our Q1 financial report. It's probably a little conservative in the sense our holiday season, Q4, the payment volume is dramatically higher. So a forward-looking number is probably higher than these numbers. And at the same time, we're not only collecting lots of data online, we are also in the process of moving, pretty push into the offline retail space. So today, if you go to Home Depot, Jamba Juice, and Toys, you can already pay with PayPal. We anticipate by the end of this year, we'll be 2 million retail locations worldwide. Pretty much wherever you can take a Discover credit card, you can pay with PayPal. And PayPal here, one of our mobile aspirations, it's launching in the US and international markets in 2013. So this all look good, right? Great business opportunity in a very strategic space, payment space. So what does it mean to data professionals like us? We have petabyte of data problems, and they grow every day. Not only we have to take all the data from our online transactions, but all the offline transactions and mobile transactions will also come into our data platforms. Okay. So a couple use cases, I already alluded to the fact that fraud, risk mitigation, be able to detect fraud and prevent fraud is a very strategic investment for PayPal, and we spend a big chunk of our big data bandwidth try to work in that space. PayPal also has a company called Bill Me Later, some of you might know. It allows a merchant to offer a customer on-the-spot credit. So some of the company I bought an HP computer from HP.com a couple of years ago, and at the end of the checkout session, you can say you can apply for credit, and they'll grant it to you instantly based on a couple of questions they ask you. Definitely, assessing credit risk is a big part of that particular business, and we use big data to make decisions about that. Making relevant offers to our customer, that's a pretty standard thing, not just PayPal. Pretty much every internet company does this thing. Right? We also use big data to track the clickstream data that we collect from our website in order to improve user experience. Right? Be able to see that which click leads to a particular user register, become a member. Which click that takes maybe a little longer to finish, that leads to abandonment. The user never register or they never complete the payment transactions. Last but not least, PayPal has a very large number of merchants who use PayPal's payment technology to allow users to transfer money. To be able to provide insights to these merchants is also a very big part of our business. Okay. So we look at this in here. So okay, these are not new, right? Not just, there's other financial service companies or internet companies do the same thing here. So what's new about the data or unique about the data that requires a somewhat different approach? Okay, so A very brief introduction. If you look at the two main workhorse for the core data processing platform is Teradata and Hadoop. Now, PayPal with its brother eBay Marketplace are implementing one of the world's largest Teradata instance, right? Big, traditional database technology. It's useful for its use cases. What we find is that when we start Hadoop, Hadoop serves as a very good complement to be a data refinery where different structured, semi-structured, or even unstructured data are being produced, refined in Hadoop, and they can be shipped over to Teradata to be presented to the user via your standard BI tools like Tableau or MicroStrategy. So to the left, we have built a little box called a data cloud. So this is the internal tool set that we have built to allow you to manage data across multiple data platforms and also facilitate data movements across these two platforms. So one thing I want to point out is that whether you're a typical companies or you're an internet company, you always run out of data center spaces. So sometimes in our case, our Teradata and Hadoop clusters are in two geographically different data centers. So one of the key things you have to be mindful of is how do you facilitate massive data transfer across data center at scale and at a reasonable cost. Okay. So if you work with Oracle and Teradata, right, your number one data abstraction where you think of it is a table. And we learn SQL at school, right? And the first thing you think about a table is it's got rows and columns. It's very intuitive. Most of data professionals think about data as it comes with a row. A row has many columns. Each column has a name and a data type. And these data types are supported by standard SQL 92 or SQL 2000 standards. And it's a standard everybody agreed upon. So whether you use a relational database as a tool or you write your own custom code, your data processing abstraction has traditionally always been using a tabular abstraction. But the physical world is a little more complicated than thinking all your data as tables, because a lot of data comes through a connected graph format. Number one example, the internet is a graph. You can think of every website being a node, and your reference to other website links are being edges. So the internet is just a giant graph with billions of nodes and edges. Next, you have from companies like LinkedIn, Facebook, Twitter, right? The social network is a gigantic graph. You are connected. I have a couple hundred friends on Facebook and a couple hundred professional connections on LinkedIn. And you can think of me being connected to these folks via nodes and the edges. For the PayPal data, the key abstraction we have is accounts and transactions. I have an account on PayPal, and I do have a transaction between myself and a merchant. That transaction represents an edge between me, myself, my account, and the merchant's account on PayPal. So if you think of a very simple example, in this graph, we have 5 nodes with a very simple account number 1 through 5. Each of the edges with a number can potentially represent a transaction between 2 accounts. I did not show the direction, but you can think about this, that these transactions and accounts form a very gigantic graph. So if you recall the stats I have alluded to, PayPal has well over 100 million accounts or customers worldwide, and they do 160 billion US dollars transactions a year. That's many hundreds of millions of transactions a year. This forms a very huge graph. If you think about graph computing, right, the number one thing, you think like a vertex. There are 2 basic operations you do with a graph. Fusion means that you take information from your neighbors and you aggregate that information with your local data and you do some computation based on richer set of input data. Diffusion means that after this computation, you take that information, you push to your neighbors. So let's look in detail what I mean. So in this particular graph, I'm about to perform a computation at the top node, at the node at the very top. So before I do that step, I'm about to receive a message from my two neighbors that's connected to me directly. So I'm going to take in my information from neighbors, couple that with local data that's intrinsic to myself. I can say that, okay, with more data, can I do a different kind of computation that provides me with more insights? So that's one of the problems we're looking into in this talk. Again, once I've completed that computation, I can push the score of the result of my computation to my neighbors. In this case, I diffuse my information to my neighbors. So one of the key things I'd like you to point out in this graph is, if you look at the two nodes that's connected to a node at the top, there is no direct link between these two nodes. So if you use a traditional computation, or like a tabular abstraction, think of it, every node as a particular row in a table. These two nodes will never know their existence because there's no direct link. But through fusion and diffusion, they can partially receive information from a node that's never directly connected to them. This is a very important distinction to make, because this really talks about, as you start to do these kind of operations in a gigantic graph, you have to think about how far you want to propagate the information from one node to another node, even though you may never be directly linked to these nodes. Okay. So we want to do graph mining. So the first thing to do is I need an engine or a platform to help me do my work. You can always try to write one for yourself, but being this is Hadoop Summit, and each one of us love open source software, I'm just like, oh, is there something in the open source space we can leverage or use? So we look at a couple choices. The first one we look at is GraphLab from CMU. This is one of the older graph mining engine. It's that particular engine is highly, highly optimized. Even the node-to-node communication, that communication stack is finely tuned for the workload. We look at that. We also consider two open source from Apache, Giraph and Hamas. A little bit about myself. I myself is a fan of Apache. I've been using Apache stuff since I started code with JDK 1.0, 1.1 many years ago. Then I always receive very high quality software from Apache. So that's a natural source for me to look for my next open source piece of software to use. There are a couple criteria we use to figure out which we want to use, right? Number one, I want this engine to be as compatible to Hadoop as possible. Why? Because I've already put all my data from different data sources, whether from an Oracle database, Teradata, my clickstream logs. The data is already on Hadoop. So if I can find something can run on Hadoop, I don't have to move data to another cluster. And I do not want to really spend the time and effort to build a second clusters. For those of you who actually work in big corporations who actually have to build up a cluster, the amount of overhead to get the data center space, setting up a cluster, get the power set up and wire them, make sure network connect is set up, that's a huge amount of overhead one has to overcome. Last thing we're looking for is integration with Hadoop. What I mean by this is, this is not MapReduce, right? This is a new paradigm to do, computation. We're looking for something that integrates natively to Hadoop so that we do not have to do a deployment like HBase. If you know HBase, what is it doing is that it reads data from HDFS, it borrows some hardware from Hadoop, and that's it. It does not really integrate with the resource manager, right? We're looking for something that, to the extent possible, that is deeply integrated with Hadoop, so we can take advantage of the advancement in Hadoop. We're also looking for something that's easy to deploy. At PayPal, right, our cluster is pretty large, a couple hundred, and soon to be over 1,000. If I have to put a new piece of software on every single data node, and my code changes rapidly, that's a pretty high tax to pay. So we're looking for something that does not require us to constantly update a piece of binary on every single data node. Last but not least, we're looking for something with a broad-based community support. So one thing I've learned throughout my career is if you want something, use open source, right? The first thing you look is how much community support it has. Does this software have enough momentum, enough support in a community to be carried forward? Since the title of this talk already gave away, right? We picked Apache Giraph based on the criteria we use. So no surprises there. Very quick introduction. This is not an Apache Giraph talk, so very quickly. Giraph implement a bulk synchronous parallel model that start with Google's Prego paper, right? It starts with every processor does a local computation, then you to go through a communication and shuffle phase. Then every single node wait at the barrier synchronization point. At this time, once every node arrives there, you complete one super step, you iterate again. So Giraph leverages some of the Hadoop existing infrastructure. It's a map-only job, so you never write to disk, to go through the reduce phase. You use Zookeeper for synchronization. And I think the latest version of Giraph used a Netty instead of a Jetty to be able to do node-to-node communication. That's to be a much scalable communication mechanisms. So I'm going to talk more about, what are the key use cases where they'll be able to leverage Giraph to solve. At PayPal, risk detection and mitigation is a pretty big business, right? Hundreds of millions of dollars annually is at stake. That's right. One of our key objectives for this particular thread of work is to be able to stop fraudsters from stealing monies from PayPal's payment network. What I mean by this is money gets in the payment network when you attach your bank account, credit card to PayPal. You're able to transfer money from one account to another, from a consumer to a merchant. At the end of that cycle, money can leave the network by going from a PayPal to a bank. Once the money is a commercial bank, you can transfer to wherever you want. And what we found is once a fraudster is able to take the money out of the network, if you don't stop them within, let's say, half a day, sometimes a couple hours, the money is gone forever. So it's very critical that we're able to react very quickly to these activities. So we have very sophisticated risk models. I mean, we have multiple models deployed in real time based on two types of input. One is the offline. We do computation in Hadoop. We do computation in a relational data warehouse. We produce data set, and we deploy these data set in a real-time, live transaction-facing environment. We also have online data. That means data happened within the last 5 to 10 minutes that hasn't quite made to Hadoop or Teradata to be fed back through the regular computation loops. So we deploy both data sets in the real-time environment to be able to stop fraudulent transactions. And traditionally, we do this kind of work based on data associated with the transaction itself. So we look at the information on the account. How many transactions has this particular user been doing in the last week or last month? What are the IPs you use? So these are pretty standard approaches. So in a very simple model, you have data that describe the current transaction. You have historical data. We feed it to a risk model. Then you make a decision whether you approve the transaction or you decline. What we see is that by definition, these PayPal data, they are connected. They form different sets of community. So our approach is that are there additional inference, insight I can derive by the fact that by not looking at a transaction as account in isolation, but by looking them through as a community, be able to deduce additional inference. If this inference provides a value, can we build a system to extract this inference in a systematic way in a reasonable amount of time? So let's look at how do we look at these real data from a graph perspective. So you have a user and a merchant. User 1 buys something from a merchant, and he pays with PayPal. Not a problem. And we know this user been with PayPal for 10 years. His all the transaction information fits a regular transaction pattern. We let it go through. So that's pretty easy. Let's say you have a new user, user 2, who just registered on a PayPal account 30 minutes ago. We have no history data about this user, his IP, his email domain, or his transaction history. And he's about to buy something from the merchant. So what should the risk model do? In a lot of cases, right, to be honest, we guess. And when money is at stake and when your model is guessing, fraudsters can always figure out a way to exploit the loophole to be able to take advantage of the system's weakness. But what happens if I see a transaction between user 1 and 2 in a person-to-person money transfer? Does the third edge in this graph help the system to derive additional insight to make a better prediction whether the transaction between user 2 and the merchant is real or fraudulent? So that's one of the use cases we're going to look at. All right. Another separate use case, you have two accounts. And they are linked together by a shared common IP. And account 1 and account 2 also use IP 2 and 3 respectively in the different settings. Their information from this graph view of the data that the system can extract allow us to, 1, to stop a fraudulent transaction, 2, let a legitimate transaction go through instead of being an overly aggressive, decline a good transaction. Okay. So the pipeline we're building, it's a pretty simple thing. There's 3 logical steps. The first one, the pre-processing, the last one, the post-processing, are just customized map-reduced jobs to be able to prepare the data and then convert data in a format the downstream application can use. The middle step is we were leveraging Giraph to do set of data processing work and then generate additional data insights. Okay. So our input data is just pretty much raw transaction data, right? And we get these data from our Oracle and Teradata database. And our custom map-reduced job take the transaction data and prepare them into a format appropriate for an engine like Giraph to consume. And we encode everything in JSON because it's just easy for both humans and Java to consume. And we use the JSON library as to manipulate the JSON processing. The post-processing is pretty simple. Effectively, once we finish producing the data set, we need to convert it into a format our downstream applications can understand. Okay, so let's take a look. In this case, you have 2 customers, or customer and account are synonymous. Sorry, we think of this way, right? So there are 4 different types of transaction from custom 1 to custom 2. So when I compute the risk score for custom 2, I take into account into that each of the transaction propagate a different risk profile into custom 2. By taking these transaction information into account, when I do a local computation on the custom 2 node, I'm able to leverage this information, be able to get a better risk assessment. And this step can continue because after the first step, custom 2 with a new risk score can propagate that new information to its neighbors. And you can imagine this form a graph that could have circles. And eventually, after enough number of steps, the risk score will converge in a graph. Okay. And take another use case, right? And we're looking at account and IP as nodes and edges. You have 2 accounts. They're linked by a common IP. So in this case, account 1 and account 2 are 2 nodes. The fact that they are linked by IP means that are there additional information I can propagate from account 1 to account 2, and vice versa, can go propagate from account 2 back into account 1. Of course, sure we can. The fact that account 1, account 2 share the same IP, we consider them to be linked. So in this case, account 1 can propagate IP2 to account 2. And vice versa, account 2 will propagate IP3 to account 1. What does that mean to us? That means if one day the user with account 2 is logged in from IP2, we consider IP2 to be a safe account by the fact account 1 has already propagated IP2 to itself, and I know IP2 is a trusted account, an IP for account 1. So these are the propagation one can do across a range of data set. It is not limited to just account and IPs. It could be email domain and some other data attributes associated with your transaction. Okay. Some of the lessons learned, Giraph being a very new project, just entered incubation last year. So I'm going to talk about what are the key lessons and takeaways by using Giraph and Hadoop to solve the problems we have. It started in Apache, as an incubation project, in early 2012, and it changes pretty rapidly. One thing we learned is that between 0.1 and 0.2, that it's not compatible. And in general, when you take on something like this, something in incubation, right, there's always a lack of knowledge. There is no dummy for Giraph book you can go read. There's everything is in the code. So one thing we did is we actually, we need to build an internal Git repo, and just, being in the traditional open source, the documentation is in the code. There's not really a shortcut, but rather read the code, understand its design. And we did port it. When we started the project, we used Giraph 0.1. We made a decision to port it to 0.2 because we see the difference is pretty big, and there are certain advantages with 0.2. One of the advantages is 0.2, I think from 0.1, it's using Jetty as a point-to-point communication mechanism. 0.2 uses Natty. It's a much more scalable way to shuffle data among all the nodes. And right now, we're using Giraph 1.0 that's officially been released last month. Okay. We need to integrate Giraph into our local Hadoop environment, and it itself poses some challenges for us. First of all, Giraph is not like your traditional MapReduce job. It requires all the mappers to be started up to keep every piece of data in memory. That means if you start a Giraph job, there's not enough mapper slot available. Either your job will not start or fail. So if you use a capacity scheduler, it's a little bit simpler, right? You just make sure that the min number of mappers dedicated to your Giraph queue is bigger than your Giraph job's needs. That's pretty straightforward. But if you happen to use a fair scheduler, where the number of mappers for a queue can grow and shrink, things get a little trickier, right? Other than the fact that you want to make sure that the min number of mappers assigned to the Giraph queue is there, you must make sure that you turn on preemption. The reason being that if there's no graph jobs, your queue slot can be used by other jobs belong to other queues. And you want to turn on preemption with a relatively short wait time. So the minute you submit a Giraph job, the preemption kicks in, effectively make these mapper slots available for your Giraph job to run. Okay. One of the biggest challenges we see while running Giraph job is about memory scalability. And in general, if you work in a shared Hadoop environment, that means you do not have a dedicated Giraph cluster per se, but you're sharing a cluster with other big Hive MapReduce jobs. And typically, we set X number of slots for the mapper reducers, and with the CPU, with the amount of memory you have per node. Typically, we have about 3 to 4 gigabytes per mapper or reducer. In our use cases, our input data is like hundreds of millions of nodes and well over 1 billion edges. When we start a project in a POC environment, where it means that we only run Giraph job with only a few developers, I happily set my memory per mapper to be 10 gig or 20 gig, right? So that's less a problem. I have a lot more memory to play with. But the minute we graduated from a POC to a general R&D cluster, that means I'm sharing this with everybody else. I no longer have the luxury to say that I can set an arbitrary memory size for my mappers. So we have to taper it down to 3, which means things that used to work in a POC environment very well suddenly stop working at all because we just don't have enough memory. So reduced memory consumption is the key. So one thing we've done is that if you look at our data sets we have, account, or even IP addresses, these data's native format is a string. And in Java, string burns a lot more memory to store in memory. So we took a trick is to convert all these data to the extent possible from string to long. That dramatically reduced the memory consumption, and its benefits are twofold. One, you're able to fit a lot more memory and a lot more data in memory. And that's important because typically we start about 200 to 300 workers. We don't go beyond that because of scalability issues. So effectively, if I'm constrained with 3 gigabytes, I am constraining about total memory available to my input data size. So I use different techniques to reduce the amount of memory consumed by my input data size. And once we finish the giraph processing, then we convert the long representation of my data back into string. So downstream applications do not have to change. So another thing we're looking at is that the capped amount number of messages we pass. So this is important in the use case that one node is propagating a message to another node. And the second node is not aggregating these neighbor messages into a single value, but keeping these messages intact and keep pushing down to its neighbors. At this rate, the number of messages being passed in the system grows exponentially. So in that case, you will quickly run out of memory, and this job will not even finish. So we come up with an heuristic to figure out a way to limit how many messages we put. So typically, we find out that one, the farther a message travels in the graph such that it's going further away, its impact, the insight this message brings to a distant node, diminish as you travel with more edges. At the same time, some of the intrinsic data value of the message can give you some hint how relevant this message is as you pass it down. So in the example I give, let's say the message is the IP, and the node is an account. So one of the value we're looking at is how many times has this IP been used with this account. The higher the number of times being used, that means the message carries more weight. So we can assign a higher score. Lower score message get filtered out, and we just drop them. So we keep the number of messages we pass in the system to a reasonable degree, such that I can pass lots of messages, not just 1 or 2 hops, but many hops in the graph. Okay. So some of the future works, right? What we're looking at is our approach is a very generic approach. You input a set of information that's based on, let's say, transactions account. These information, you can look them through isolation. But by looking at the connected nature of these data and process them with a graph engine like Giraph, we can derive additional insight. Effectively, each of the data entity will have a richer data set. And that information can be used by your data scientists, whoever use data engineers to be able to derive additional insights for whatever use cases you're going to use. And something we're very excited about, I think there's a talk tomorrow on Giraph that we're looking forward to leverage Giraph on Yarn. So a lot of constraints we have in terms of memory scalability is because of the fact we're still running on Apache Hadoop 1.0. You pretty much fixed amount of resource you can devote to each mappers. I think Yarn would be a very good step forward for us to asking for the appropriate size amount of resource a particular Giraph job would need. Another thing we plan to work on is that today, we run about 250 workers, because the amount of shuffle data communication overhead grows exponentially as you increase the double or triple number of workers. We're looking to that, can we increase the number of workers to be able to address the problem with a larger input data size? And that is something here we wish to work on such that Giraph be able to thrive on a scalable platform like Hadoop. So, okay. And then I have some time at the end for some Q&A. And so, okay. Okay. One thing we do is there's a mic in the hallway, so if you have questions here, we're taping this. Could you step up to the mic? Okay.
Hi, I have a question about the risk you calculate by using the community or the graph. Do you eventually just is it a function of the intrinsic graph of the nodes that are around that node?
Okay.
I mean, if you're calculating the risk of A, and then to calculate the peer risk, you go to B and you go to C, the result is going to be a function of the intrinsic risk of B and C, right?
And that is correct. And the question is, when you calculate, a risk node A and its neighbors on B and C, is a function of the intrinsic of in this case, it's a function of A and B and C. But amount of weight node B and node C contribute to the risk of A is based on one, based on the use cases, two, based on the particular risk models. At PayPal, we have different kind of risk models. And based on the information you're propagating from B and C, which are neighbors of A, into it, based on that particular risk, particular models, we do different kind of propagation.
Okay, thank you.
Okay.
I was wondering how long you think it'll take you to leverage Giraph on Yarn, and thoughts from you about how long or how fast, how quickly you think you could have done this if you already had Yarn in place when you started, as opposed to using Hadoop 1.0.
Okay, so the question is, how long would it take if we were to build using Yarn instead of doing Hadoop 1.0? So let me give you a little bit of context, right? Before you talk about Giraph, just say, could we have done this in MapReduce, right? And at the end of each step, you write your data to HDFS, and using a file system as your communication medias. Okay. And the question is yes, and we. First of all, for this one, and actually using a MapReduce approach to do this kind of graph computation takes about 10 to 50 times longer. Two is that I think with Giraph, we're able to unshackle the memory limitation we have. This has a pretty big impact. I think we can go much further where we spend more time trying to improve our graph algorithm versus try to overcome the system limitation Hadoop 1.0 imposes on us. So we are at the end of the time, but I'll be available. There'll be questions. Feel free to come up and talk. But thank you very much.